Hello, I am SP Basavaraj. This presentation for you is a limited presentation regarding the experiment LCR Series and Parallel Resonances. This is simply to help you having a better preparation prior to your practical examination. You have already done this experiment once in your regular lab class. Now I am providing here just a quick glance of the apparatus, a review of the setup and of the procedure. As a recap from your regular class performance, you can recall that to begin with, you had built up the LCR series and parallel circuits and then studied their frequency responses by feeding an AC into the circuits. Afterwards, from the graphical plots, you got the two resonance curves from which you had evaluated the inductance values of the inductor. Then from the series resonance curve, you went on to evaluate the bandwidth and then the quality factor of the resonance. Now you will be quickly going through all these like a revision visually. Let's start with the apparatus you've used. First, the circuit unit and the connections in it. This is the LCR circuit unit. The white body on which the circuit along with the other components are provided is called the chassis. An AC milliammeter is provided on its upper elevated portion, below which there are terminals for connection. Below that, in the mid part of the chassis, there are two inductors L1 and L2, three resistors with the resistance values, and three capacitors with their capacitance values mentioned. The inductance values of L1 and L2 are unknown. Now, among the resistances and capacitors given here, you need to choose one each from each category for making the circuit. Let's choose L1 for the inductor with unknown value, 1 kilo ohm resistor and 0.01 microfarad capacitor for the circuit. The actual circuit used for both the resonances is provided in the lower part of the chassis into which the required connections are to be made. We are studying here two types of resonances. Part 1 series resonance and part 2 parallel resonance. First, let's take up part 1 and go through the series resonance. In the series resonance studies, all the three components, namely inductance L, capacitance C, and resistance R, are connected one next to the other to form a closed circuit like a chain with an AC source and an AC milliammeter. There are only 5 connections to be made. Number 1. Connect the AC milliammeter to the two terminals at M and N in the circuit. Here the polarities don't matter as the current is AC. Number 2. Connect L1 across the symbol L in the circuit. Number 3. Connect 0.01 microfarad capacitor across the symbol C between L and R. Number 4. Connect the resistor 1 kilo ohm across the symbol R as shown. And lastly, number 5. Connect the AC output of the signal generator to the points X and Y. With these connections, L, C and R are connected in series and the connections for studying series resonance is completed. Please note, there is no connection to be made across the other C, which is at the extreme right in the circuit. Ignore its presence at present. After you complete the connections as described, the setup looks like this. In this photo, you can see the experimental setup made ready for investigation with actual connections. Now switch on the circuit unit and the signal generator. Let's see about the signal generator that provides AC current to the circuit. There are different types of such generators in different institutions. However, their mode of operation is practically the same. It must be possible to understand the working of any other type of generator by following the explanation for the one I am dealing with here. The signal generator is also called AC source or a function generator or simply as an oscillator. Let's know about the various controls and operations in the oscillator now I am dealing with. This is the image of the front panel of the signal generator I am describing here. At its lower part, you see two push buttons. They are the power attenuation buttons. When the button is held in like this, it is in the on state. For example, here the 20 dB attenuation button is in. hence the attenuation is active. Since we do not want any attenuation, keep both the push buttons in the off position like this. Now you see here both the push buttons in the off position. Let's know about the frequency variation control knob. On the top of the panel you see 4 knobs. Turn all the knobs to the respective minimum positions. This is the frequency control knob by turning which we vary the frequency. The next 2 knobs, namely the pulse width and the DC offset knobs, have nothing to do with the sine waves and hence simply ignore them. The last one, named amplitude knob, is actually the current control knob. The frequency variation should be started only after setting this current control knob at a particular initial position. Its position should be left untouched till the frequency variation studies are completed. Though it is suggested to keep the position of the knob at 50% of the maximum amplitude position, you may do it the way how you did in your regular class. Now let's see about the waveform selection. This is the waveform selection button. Switch on the unit. As per the display in this case, the unit can give square wave, but we want sine wave. Focus your attention in the display which is now showing as SQR and keep pressing the button for waveform till it shows as sine. The unit gives sine wave output in this setting. Now let me explain how the frequency variation is done. You can see here by turning the frequency control knob how the frequency is continuously varied and stopped at the desired value. But between the minimum and maximum positions of the knob, the frequency variation could be done over a range, such as in the range from 0.1 kHz to 1 kHz or 1 kHz to 10 kHz and the likewise. Select the actual range as per your tab column listing of the frequencies. It could be done by means of a range selection button as follows. At the bottom part of the panel, next to the waveform button, you see 2 push buttons. They are meant for selecting the range. The one with the arrow pointing towards your right increases the frequency range by a factor of 10 by pressing it like this. Ignore the third digit in the display. Please note, since the frequency knob is set at its minimum to begin with, it is the starting frequency that you see in the display. By turning the frequency control knob, the whole frequency range could be scanned starting from this minimum frequency. 0.1 kHz to 1 kHz is in one range, and in the next range you have frequencies available to you from 1 kHz to 10 kHz. The other button with the arrow pointing towards your left helps to select a lower frequency range down by a factor of 10 for each push of the button like this. You see here how the frequency changes from 10 kHz to 1 kHz, then 1 kHz to 0.1 kHz for the first 2 consecutive push button operations. Note, it is the range that is changing here and not the frequency. The frequency selection is done by adjusting the frequency knob as explained earlier. Now about how the AC output from the signal generator is fed into our LCR unit. Here at the right bottom corner is the connector from which the output is taken. One end of a coaxial cable is connected to the signal generator. You can see here its free end is having 2 connector pins which when connected to our experimental unit feed AC into the LCR circuit. Now let's know about how we make observations. First, turn the frequency knob to its minimum position. Looking to the starting frequency in the tabular column, select the frequency range in the signal generator. By operating the frequency knob, adjust the frequency of the oscillator to the first frequency value in the tabular column. Note down the corresponding current reading shown in the milliammeter. Similarly, follow the currents for the successive frequency values in the tabular column. This procedure is followed till the last reading is entered in the tabular column. You can observe that the current rises slowly from a low value and rapidly reaches a maximum and decreases also rapidly. However, you will be continuing your observations a bit beyond that stage also for the sake of seeing symmetry in the rise and fall of the curve. Now, I will tell you one extra optional observation that you might not have made in your regular class, but the one which is likely to help you in improving the graph that you are going to plot. It's this. Adjust the frequency of the oscillator to become equal to the frequency value corresponding to the maximum current in the tabular column. Watching the current in the milliammeter, vary the frequency and check when the current becomes maximum. If this current is higher than the one in your tabular column, it will be for an odd value of frequency that was not listed in that stepwise increase of values. Then note down this new maximum current value and the corresponding frequency value as extra readings at the end in the tabular column, which of course be used while plotting. Now what next? The series resonance observations are completed. However, retain all the circuit connections without disturbing. Plot a graph of current versus frequency. You get roughly a bell-shaped curve. On the curve, the current corresponding to the topmost point is Imax and the corresponding frequency is the resonance frequency Fr. Mark a point at the current axis corresponding to the value 0.707 times Imax. From that point, draw a horizontal line parallel to the frequency axis. The line crosses the curve at 2 points A and B. The two frequencies Fa and Fb that correspond to these 2 points on the lower side and the higher side respectively on the frequency axis are called the lower and upper cutoff frequencies in order. The difference in values between the two is the bandwidth delta F. Let's know about calculating the inductance L and the quality factor Q. Calculate the unknown value of inductance L of the inductor by using the equation L equal to 1 divided by 4 pi square Fr square C. The unit of inductance is Henry. By referring to the graph, calculate the quality factor Q graphical by evaluating the ratio of Fr to delta F. It's a number and doesn't possess any unit. For the sake of comparison, quality factor is also estimated theoretically by using the equation Q estimate equal to 1 by R whole thing divided by square root of L by C. The agreement between the two must be satisfactory. Now let's take up part 2 and see about the parallel resonance. You have retained all the connections in the circuit made before. So you are having it all the same way as it was when you completed the series resonance observations. This is how it was symbol wise, and now just make only the following two changes. Number 1, pull out the ends of the connectors across the capacitor from the points D and E and insert them at the points J and K across the new position for the capacitor. Number 2, provide continuity between D and E by connecting them directly by using a connector like this, which we call as shorting. You can recognize that the inductor L and the capacitor C, which is at the end of the circuit, are now in parallel connection, just right for making the parallel resonance studies. After you complete the connections as described, the changes made in the connections can be seen here in this image. All other connections remain the same. Setup wise, it looks like this. The connections for studying parallel resonance are now set, and you can start the observations. As you did in the earlier case, vary the frequency in steps as given in the tabular column and note down the corresponding current. Plot a graph of circuit current versus the frequency. This time you get a valley-shaped curve like this. The current corresponding to the bottommost point of the curve is I mini, and the corresponding frequency is again the resonance frequency Fr, which will be almost the same as the one obtained during series resonance. Using this value of Fr, Calculate the value of inductance L by using the same equation that you used earlier. Take the average of the values of L found by both the resonances, and that's one of your results. With this, we have come to the end of this video on LCR series on parallel resonances. Further, as an aid for your reference, I am providing here some more information in the next few slides. Here you find the details regarding series resonance. Here about the parallel resonance. The circuit diagrams and the related graphical curves are seen here. Please note, in the tabular column 1, the frequency values listed here are only typical. You must carry out the observations with the values of frequencies with which you did the experiment in your lab class. After following this video, if you have some questions in your mind or if you like to have any clarifications, you may mention them in the comment section below. Remember, listen to the instruction given by the examiner carefully at the start of the examination. As a preparation before the examination, practice drawing circuit diagrams, figures of graphical curves and the tabular column details. Memorize the formulas. Make a calculation once of the inductance, Q graphical and Q estimated by taking the values from your physics practical record. That's all, students. I hope you found this video helpful. Do have a great performance in the practical examination. With this, the basic matter I intended to explain to you regarding the LCR resonances comes to an end, I would like to conclude this talk with a bit of following information. One is this. You know, LCR circuit and its dramatic response to the variation of AC frequency constitutes a great topic in physics under the branch of electricity and magnetism. I am working on collecting information on its historic growth, who discovered what in it, and all such things. I will be telling you about the history of what all happened that led to the formulation of LCR circuit. It shall appear in the YouTube in this channel in the due course of time. Another one is this. It's regarding the shape of the resonance curve, which I will be explaining now. It's a very well known fact that the resonance curve is bell-shaped, but many of you have got the result perfectly alright, but the curve was not really bell-shaped. Among you who are wondering why the curve they got was not really bell-shaped, they can now understand the reason behind it. I will tell you about that. The reason is simple. I would like to explain it this way. Now you must keep the tabular column page in your practical record open in front of you. As you glance through the listing of frequencies in it, you will see in the beginning that the frequency changes go in smaller steps, such as 100 Hz or maybe 500 Hz. As you progress into higher values, the frequency starts making longer strides of no less than 1 kHz. In fact, if there is any reason to continue further, then it would require hopping the frequency changes in gaps of 5 kHz and then even jumping through 10 kHz every time. That's the nature of the dependence of LCR circuit current on frequency. What kind of dependence it is? Since equal rise in frequency is not resulting in equal rise in current, obviously the dependence is not linear. Is the dependence exponential? No. Then is it happening randomly? Not at all. A physical change always follows some kind of mathematical order. If you follow the kind of increase in frequency required to rise the current by equal amounts, it follows a particular pattern of increment which is known in mathematics as logarithmic. On this basis, we say the dependence is logarithmic. Since the dependence on frequency is logarithmic, you can have the natural view of the change in current if you plot current against log f, that is logarithm of frequency. then you will get a nice curve in the bell shape. But when you plot a graph of current versus frequency without taking logarithm of frequency values in the scale, the curve will not provide you the view of its natural dependence. Though you see the resonance peak perfectly alright, the overall view of the curve will not have the well-known nice bell shape. Now for you to compare, I am providing here in the next slide the images of both the types of curves that I got. Perhaps you can also try plotting the current versus log f graph with your observations. Here you see both the curves. The one towards your left side is plotted with the values directly from observations. The other one is plotted after converting the frequency values into log f values. It's a graph of current versus log f. You may see that the log f curve resembles the bell shape more in a natural way. There is an alternative to this task of calculating log f and then plotting. It's achieved by using what is known as semi-log graph sheet. Its structure is different. Along one of its two axes, the lines are not uniformly distributed. The lines become closer and closer progressively so that the gap reduces logarithmically. Along the other axis anyway, it has markings at regular intervals. If you use a semi-log graph sheet, you can directly go for plotting the frequency without having to calculate the log f values. I am also making a video on what's a semi-log graph sheet and how to make use of it, which shall be in the YouTube shortly. However, please note that it is not required to use a semi-log graph sheet for your plotting as per VTU syllabus requirement. But you may choose to do it only to understand how it provides a ready-to-use assistance to plot a logarithmic variation. If you were a student of electrical or electronics or telecom branches, this provides an opportunity to learn about it, the knowledge of which shall help you later in the practical classes of higher semesters. Thanks for watching.